All right, so we're gonna go back here to chapter 7, which we talked mainly about different ways to classify reactions. And remember that in chapter 7, there was basically there is two basic big categories of reactions, which are our double displacement reactions, which take care of basically precipitation reactions and acid and base reactions. And those two reactions, as we talked about, take care of two of the three reasons why a reaction takes place. Precipitation reaction, because a solid is made, typically an acid-base reaction. Then water is basically what you're formed. The other part of the chapter that we talked a little bit more in detail as well is the other one, which is redox reactions, which pretty much covers electrons being transferred and all the more specific classifications like combination, decomposition, single replacement, combustion reactions. So here we're going to focus back onto our double displacement reactions. And a lot of double displacement reactions result from a mixture of solutions, and a solution is a homogeneous mixture of basically two parts: the solute, which is the smaller part of the solution, and the solvent, which is the larger part of a solution. And when we talk about aqueous solutions, they are the guys that get that aqueous symbol next to it. We might have touched upon it, but again, just a reminder that there is a difference between the liquid symbol and the aqueous symbol. Once again, something that gets the liquid symbol is a pure liquid. So again, if you have something just like water by itself, that would get the liquid symbol next to it. Aqueous is really, as it mentions there, a mixture, which means you have to mix two things together. So if we took some sodium chloride, which is a solid, it would dissolve in water. And again, that would make a sodium chloride solution that would get the aqueous symbol next to it. The solvent in a lot of cases is water, but it's not always the best solvent, as we'll talk about in some later chapters. But water works really well for ionic substances, also works really well for polar substances because they can interact well with one another. But again, water doesn't work so well, for example, for non-polar substances. They do not work very well. So typically, if you see something with the aqueous symbol, that is a solution. How do you know what the solute is? It's really the name of the solution. So sodium chloride solution, the solute would be sodium chloride in that particular case. So whatever the name of the actual solution is pretty much what the solute is. And if it's an ionic compound, there's probably a pretty good chance that the solvent is going to be water, is probably what was used to make that solution. So again, a solution is aqueous. It is something that's made by really mixing two things together where they really dissolve. Homogeneous means everything looks the same throughout. So when we talk about electrolytes, what we might have talked about previously, electrolytes are substances that when they do dissolve in water, they conduct electricity, and that's because they do produce ions. So these are substances that produce ions. And it's really the presence of those ions which help make it conduct electricity. There are things that are strong electrolytes. And again, they basically 100% break apart into ions. So things that are strong electrolytes will completely break apart into ions. There'll be none of the kind of whole units still together in the solution, and that's why they're able to really conduct electricity really well. So for example, like we just talked about there, our sodium chloride solution, when we have a sodium chloride solution, it is going to 100% break apart into sodium ions and chloride ions, which means when you look at that solution, that's pretty much all you got floating around in that solution. You have none of the whole unit still together. It is completely dissociated and broken apart into ions, which is why it's a strong electrolyte, why it conducts electricity really well as well, because there is a ton of ions floating around in that solution. So that helps it conduct electricity. There's also weak electrolytes. And weak electrolytes will actually stay together mainly. but break apart a little into ions. Take 3, here we go. All right, so as I was saying 3 times already, weak electrolytes will basically stay together. They will, though, break apart a little bit into ions. So weak acids, weak bases, for example, are very common weak electrolytes. We could recognize these by really two-way arrows. For example, hydrofluoric acid is a weak acid, which is a weak electrolyte. In solution, you mainly have this guy, but you have a little of these guys. So if you were to look at that solution, you would mainly find those guys still together, but they will break apart a little bit and produce a little bit of ions in that particular solution. Again, you could also recognize it usually written as sort of a two-way arrow heading in both directions. A non-electrolyte will still dissolve, but will not conduct electricity, and that is because it does not have any ions present. So even though it will go into solution and dissolve, it's usually more of a covalently or molecular sort of compound where they're sharing electrons, so there's no ions being produced. So no ions being produced will not conduct electricity. A weak electrolyte could still produce some electricity or conduct electricity, because it does have a little bit of ions that are basically breaking apart. So some strong electrolytes, sodium chloride, potassium iodide, calcium chloride, pretty much anything that's an ionic compound in most cases are going to be a strong electrolyte. Also strong acids and strong bases are also strong electrolytes. Strong acids, kind of put a list of some of those strong acids, which are a good list to know: hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, hydriodic acid. So this list of 6 strong acids are very common, strong electrolytes that you come across. They will completely break apart. Some strong bases are pretty much our guys from group 1 and 2 on the periodic table that contain hydroxide, things like sodium hydroxide, potassium hydroxide. And that's really why they're considered strong acids and strong bases, because when they do go for a swim, they will basically 100% break apart into those ions. So they're able to produce H plus and OH minus, which is kind of the definition of an acid and a base in that case. So I would say, just in general, if you come across some acids and it's not one of these guys on this list, you could probably make a pretty good assumption that it's going to be a weak acid and it would not break apart in solution. And that's going to be a little bit important as we talk about writing certain types of equations as we go through it. Any questions on it up there? So as I mentioned, water works really well for a lot of ionic compounds, and it is a solvent for most ionic compounds, most polar things. It's not very toxic or anything like that, but it works very well because of some of the bonding aspects of it that we talked about. Water is a polar molecule, which means, again, it has a negative side and a positive side. The oxygen more the negative side, really the hydrogen's there more the positive side. So that works well with ionic compounds, because when ionic compounds, like say a sodium ion, goes for a swim, it's going to be surrounded by water, and it's going to be attracted by that electrostatic attraction. Opposites attract. The oxygen side of water will basically be able to surround it. And the same thing with the negative ion there. It will also be attracted to water, but it would actually be attracted to the hydrogen part, which is the more positive part of water. And actually, that is, again, how pretty much an ionic compound is able to dissolve. It goes away. And remember that it is just a physical change, right? When we dissolve something and make a solution, we saw that in a couple of experiments early on, where you took your evaporating dish, you heated it up, right, and you evaporated off all the water, and you saw the solid return. And that is because you got rid of all the water that was in the way. So Water, because there's so much of it in actually a liquid there of the water as it's going to dissolve, it's able to basically pluck off these ions from one another. Before it starts, the ionic solid is a solid with all the ions really attached to one another, but because of the sheer volume of water, they're able to really surround each of the ions kind of and pluck them off. It also prevents those ions from coming back together, which is ultimately what they want to do, because that's a really strong attractive force. We can't see it anymore, right? But it is still there. Something like salt, when it dissolves in water, it's just so much water, we really just can't visually sort of see it anymore. Again, that's why we talked about it earlier on, that it is a physical change and not a chemical change, because we can retrieve back both the water and the salt in this case, right? If we wanted to separate it back out, like we talked about. And that's what happens, as we were talking about, when you start to heat it, you evaporate off all these waters. And now there's really nothing in the way for those two ions. They're going to be super attracted to one another because of their charges to basically come back together. But in the presence of all those water molecules that are in there, they're able to really kind of separate out each of the ions from each other and keep them from coming back. And ultimately what we see is it disappears, basically the salt, right? As you're dissolving it, you help it out when you go to dissolve something, right? Because you stir it most of the cases, right? So as you're stirring, you're throwing tons of water molecules all over the solid ionic compound. You're also providing energy, which helps it obviously dissolve as well. So all those things help in the process of something dissolving. This process where these ions get surrounded by water is sometimes referred to as hydration. And again, this is pretty much what happens in any ionic compound when you go to make a solution and you go to dissolve it. This is essentially also pretty much why we write aqueous next to it, so we don't have to write all the waters. So the aqueous basically implies that those ions are in solution and they are surrounded by water, basically. And that's, again, what that aqueous sort of symbol represents. Otherwise, we would write, you know, whatever the ion is with like a bunch of waters attached to it. And before you know it, the equation gets really, really complicated. So a lot of times we don't do that. We just kind of put the aqueous next to it to imply that they are in a solution and surrounded by waters. So as I said earlier, acid and bases are strong electrolytes. And again, those list of 6 that I put up there just a second ago are really good ones to know, and you should kind of commit those to memory as you go through your chemistry career. And it does make sort of the idea of, is it a strong acid or a weak acid, pretty easy. If it's just not one of those, like I said, it's a pretty good assumption it's going to be weak. So once again, in solution of hydrochloric acid, which is a strong acid, you pretty much have 100% those ions floating around. Once again, we have none of that strong acid still together. And that is why it's considered a strong acid, because all it has to do is go for a swim and it's going to produce a ton of H plus in the solution really quickly. And that's pretty much your definition of an acid. This is acetic acid, like you find in vinegar. And when it goes into solution, it's actually a weak acid. Again, it's not one of those 6 that was on that list. So safe bet that it's a weak acid. So we're going to produce a little of these ions. And once again, it's still considered an acid because it can produce some of the H plus in solution. But this is, again, mainly what you're going to have in that solution. So if you were looking at it once again, you're going to have these whole units still together. But you will have, you know, a little bit of acetate floating around, a little bit of H plus floating around, but mainly it's going to stay together. That reversible arrows, again, means that this thing will eventually reach chemical equilibrium. And what that means is the forward direction, which is the arrow that points to the products, is sometimes referred to as the forward direction. At some point with weak electrolytes, what will happen is the products will build up enough products that they will actually recombine and make the reactant. So it'll kind of go backwards, this type of reaction. And that's what's referred to as the reverse direction. And what it means when it reaches chemical equilibrium, which you'll learn a lot more about when you take Chem 1B, it doesn't mean that they're equal on both sides. And sometimes people have that idea that it says equilibrium. So we've got equal amounts and stuff on both sides. But really, when they talk about chemical equilibrium, what they're talking about is actually the rate and the rate of the forward reaction will equal the rate of the reverse reaction. And that's basically what it means when it reaches chemical equilibrium. So essentially what that means is just as quick as it goes to products, those guys are going to recombine and come the other way. And what that means is it doesn't necessarily mean that you have an equal amount on both sides of the arrows, but it means wherever they are in terms of their concentrations or even pressures, if you're talking about gases, is they're going to lock themselves into those concentrations, because just as quick it goes one way, it goes back the other way. So everybody basically is able to maintain their concentrations at that point when it reaches chemical equilibrium. For our purposes here, if you could recognize it as a weak acid or even a weak base, it's important to know that it will mainly stay together instead of breaking apart into ions like we have with our strong electrolytes. Yes, sir. Say again? It will most likely break apart into ions, definitely in water. And it can also in any liquid that it's soluble and that it will mix well with. But water in most cases, for anything that's ionic or anything that's an electrolyte, that break apart into ions is pretty good solid. Yeah. Other questions? Okay. All right, so as we talked about last time, there's these two big classification of reactions, our double displacement and our redox. And once again, our double displacement we could recognize as two ionic compounds coming together. And again, we're going to switch partners on the other side, and that will give us A and D and C and B. And again, one of these things can be a solid, which gives us a more specific precipitation reaction. R1, for example, could be water, which is more of a acid-base reaction that we talked about. Again, our redox is about electrons being transferred. And again, that covered all those other classifications we talked about: synthesis, combustion, decomposition, and single replacement. So as I mentioned earlier, we're going to focus here on the front part about our double displacement sort of reactions here and what's happening. So let's take a look at it, and we're going to talk about, how we know if we do get a solid or we don't get a solid when we sort of mix them together. So let's talk about that precipitation reaction. A precipitation reaction is characterized as some type of solid that is being formed. A precipitate, which is sometimes abbreviated as a PPT for precipitate. It does not necessarily have to be a rock hard solid that is formed. Again, it could be something that gets cloudy, some stuff floating around that wasn't there before. But it's usually a result, for example, of mixing two solutions together, very much like what we did in that last experiment where we made all that yellow, right? We mixed a couple of things together and we formed that yellow solid, which was a precipitate. Precipitation reaction usually involves ionic compounds, and upon that sort of double exchange that occurs, we get some type of solid that happens as a result of the two ions basically coming together. So if we look at one, it's very similar to the reaction we did. Actually, I think it might be the reaction we did, actually. Led to nitrate plus our sodium iodide. We can recognize this once again as a double displacement, as that is positive, negative, positive, negative. And again, we're going to switch partners on the other side. As we also talked about in this chapter earlier on, we want to make sure definitely that we end up with the right formulas on the right-hand side of the arrow. The result of this is we will get that lead to iodide, which, as you know, is that yellow solid that will form as a result of this reaction that takes place. So what we see up here is what is referred to as the molecular equation, and that is the equation that is written where we see everything in their correct formulas. We also see their states. We can also write what is really sort of happening in this reaction when we sort of mix these two solutions together. So this guy here is aqueous. And when we do put these two solutions into this beaker or whatever it may be that we're going to mix it in, it really will not stay together, those particular compounds, because they are strong electrolytes. So when they go for a swim, what happens is really the lead ion is freely floating around in there. We also will get a couple of the nitrate ions that will float around. And that's basically all coming from our lead to nitrate in this particular case. Same thing will happen here with our sodium iodide. That is a strong electrolyte, and that will give us 2 of the sodiums. And as you can see, that coefficient gets distributed there, 2 of the iodides. Now we do make this solid on the other side, and the only way for it to be a solid is it actually needs to stay together in that solution. Otherwise, it would just be ions that are floating around freely in the solution. When we look at the sodium nitrate, which is this guy, it's a strong electrolyte, and we will have a couple of sodiums and a couple of nitrates that are broken apart here. And this equation, which is sometimes referred to as the total ionic equation, or complete ionic equation, depending on your book, describes basically what happens when we put these 2 solutions together. So when we put these 2 solutions together, essentially we have our lead ions floating around, nitrate ions, sodium ions, and iodide ions. And again, these guys are basically free floating in that solution. What happens though is, as you can see from this equation, we actually do make a solid, which means that while they're floating around, there's going to be an attraction, frankly, between these 2 guys. And they're going to come together and make a solid. Guess I could have went with yellow, which would have been the right color, but we'll go with green in this case. And when we look at a total ionic equation, it's basically describing sort of what is happening in that particular solution. Now, once we write the total ionic equation, we could always find ions that are on both sides of the arrow that look exactly alike. And in this case, we have a couple of nitrates. We also have a couple of sodiums. And these are ions that, like I said, look exactly the same. They actually should be the same amount on both sides. And these ions here that look exactly the same on both sides of the arrow, these are what are referred to as spectator ions. And if you are a spectator, you are doing what? You're just watching, basically, right? And that's what these guys are doing. As you can see from my picture, they're just kind of floating around, and they'll still be floating around when this is all said and done. And what we do with spectator ions is you could think of the arrow as like an equal sign. You could subtract those guys from each side, and what happens is they will essentially cancel each other out. And they should completely cancel each other out if they are spectator ions, and that means you should have the same amount on each side of the arrow. If you find yourself doing this and you do not have the same amount on both sides of the arrow, you probably didn't balance your equation right or something like that. So something is wrong along the way. What that actually leaves us is a third type of equation, which is essentially what is really going on in this reaction. What is really going on in this reaction is the lead ion from the lead to nitrate is going to find the iodide ion here. And they're going to come together to make this solid, which is really the main thing that is happening in this reaction. And this is what is known as the net ionic equation. And the net ionic equation is pretty much the equation that tells you pretty much this is what's happening. What's happening is lead, iodine is going to come together to make that solid. The reason that's really important is That is the whole reason behind why this reaction is taking place. Is that formation of that solid. So it's a formation of solid. The sodium, the nitrate is still floating around. What's going to happen again? These guys are going to come together, and we're going to make a solid. We'll still have these guys just floating around in the solution at that particular point. Any questions on that? So these are three types of equations that are commonly used, definitely with double displacement reactions. Could also be used with single replacement reactions as well, and redox reactions, but mainly for double displacement reactions. The molecular equation is the equation that basically just shows all the formulas, everybody together in their proper sort of compound and formula. The total ionic equation shows really what is happening in that solution. We break apart, by the way, when we get to the total ionic equation, we break apart completely anything that's a strong electrolyte. And we keep together anything that is a weak electrolyte. So if you had a weak acid or anything like that, you would keep it together. So for this total ionic equation, anything that is a weak electrolyte, anything that is a solid, a liquid, or even a gas in most cases will all stay together. So you would not break them apart if you had any of those things in this particular reaction. If they're all strong electrolytes like we have here, all pretty much ionic compounds, you do break them apart completely, as when they're in solution, they're just ions that are floating around. Any questions on that there? All right, so let's take a look here. So once again, this is our guy breaking apart into our total ionic equation, and anything that's a strong electrolyte should be broken apart. And as we see in these examples, if you do have a coefficient, that coefficient, when you go to break it apart, should also be distributed to everybody. And also, if you have a subscript, the subscript comes to the front when you break it apart into the ions. So again, that's really important to keep everything balanced, is to kind of move those subscripts and coefficients along so that everything completely cancels out. Again, our spectator ions always going to be found on opposite sides of the arrow and should always be the same amount on each side. Again, if they are not the same amount on each side, then you did not properly balance it. And that gets us to our net ionic equation. So oftentimes we do use net ionic equations to really cut to the heart of what is happening in that reaction, to display, in this case, that is really this solid that is being made. It also is balanced, as you can see, same number of elements on each side, and actually the same overall charge on each side. A couple important things about these two equations, which is our total ionic equation and our net ionic equation. Anything that is an ion has charges, yes? So anything that you write the formula for ions, they do need charges. So make sure you have the charges when you do that. It's a very common thing. People don't write charges on net ionic equations or total ionic equations. And just like normal as well, anything that's staying together, if it's an ionic compound, will not have a charge, right? So it needs to balance out to zeros. But when you do write the formulas for the individual ions, they do need to make sure that you have the charges that are involved. Okay. So how do we know when we put things together, will we get a solid? Will we get something that's aqueous? And we can use the solubility, or really what's known as solubility rules, to help us predict that. The solubility of a substance is the maximum amount that will dissolve in a given quantity of solvent at a temperature. It's basically broken up into three categories. There are things that are soluble, which means that they will mix, everybody will dissolve, you will not get a solid. So if something is considered soluble, those are the guys that get the aqueous symbol next to it. It means you basically made a solution, so no solids should happen. There are things that are insoluble, which means when you put them together, they will not mix basically, and we would expect a solid to form. So things that are insoluble based on the solubility rules are things that will get the solid in those equations that we write. And things that are slightly soluble, which you might come across occasionally, is pretty much what the name sounds like. There is some degree of solubility, but most people consider things that are slightly soluble to be more like it being insoluble, so leaning more towards the insoluble side. I will say that, as you'll learn if you go off to Chem 1B, you know, even things that are technically based on solubility rules to be insoluble, everything has some degree of solubility, even if it's like super small. You know, you get like a super small amount of everything to dissolve. But seeing they're so small, certain things are so small, when they can dissolve, that's still considered to be insoluble and really not really soluble. So most of the time you'll come across things that are soluble or insoluble. And like I said, if you have something that's more on the slightly soluble side, then you could probably lean that more towards it being insoluble. So let's take a look at some of these rules here. First off, these are things that are typically soluble in water, which means if you have any of these things in there, we would expect it to make a solution. So these are things that typically will be aqueous and not make a solid. Pretty much if you have anything in group 1 on the periodic table, and you see anybody from group 1 in the formula, you could pretty much stop right there and you can write aqueous next to it. It will be a solution. Similarly, if you have anything that has ammonium in it, so if you see NH4 in the formula, you also could pretty much stop at that point and it will be aqueous no matter what the situation is. Things that contain nitrate, chlorate, or perchlorate are also soluble. So once again, if you see anything with nitrate in the formula, you could automatically just lay up a aqueous symbol next to it. Things that contain chlorides, bromides, and iodides, those are also soluble. But unlike the others, there are some exceptions. So these guys here are typically soluble, which means they will get the aqueous symbol next to it. But there actually are a few exceptions. And the exceptions here are if any of those guys are hooked up with silver, that is mercury 1, by the way, and that is lead 2, then they are going to be the opposite of soluble, which means they will be insoluble and they will get a solid. So there are certain things that are, for example, soluble in everything, but there are some exceptions. The first few that we just read off there from the table, there are no exceptions. So it doesn't matter. As soon as you see them, you're good. But if you have chloride, bromide, iodide, you do need to make sure that it's not hooked up with silver, lead, or mercury. And if it is not, it will be soluble. If it is silver, lead, or mercury, then it will be insoluble. Most sulfates are soluble, except calcium and silver sulfate, which is slightly soluble. And again, that slightly soluble means kind of insoluble. And barium, mercury 2, and lead 2 sulfate are insoluble as well. So again, if you have sulfate, it's going to be soluble or aqueous, unless it's hooked up with any of those guys, barium, mercury, or lead, then it's going to be insoluble, basically. Any questions on those rules there? Now, there are some rules for things that are typically going to be insoluble. So these guys on the list here are typically things that will get the solid sort of symbol next to it. Hydroxides are typically solid, except if it has basically group 1 attached, or ammonium. So if you have group 1 attached, it's not going to be soluble. Barium and calcium are slightly soluble. And again, slightly soluble considered insoluble. Carbonates, phosphates, and sulfides are insoluble, except if they're hooked up with group 1 and ammonium. The good news is it's really kind of the same rules as the first slide. If you have group 1 or ammonium in there, they're going to be soluble. So even if it happens to be with any of these guys, they would be. Any questions on that there? Here's another sort of version of that table. Again, things on the left here are soluble. So anybody on the left here will be aqueous, but if it's anybody over here, they will be solid. And these guys will be solid if it's anybody on the left, except if it's anybody there on the right. So these are some solubility rules to say you should know. I want you to know those. They will not be providing that for your future chemistry career throughout here at Saddleback. So you should know those things. Any questions on that? So let's take a look at some things. Let's say I threw together a little sodium carbonate with let's see with some barium nitrate. I want you to write the balanced molecular equation, the balanced total ionic equation, the balanced net ionic equation, and identify the spectator ions. All right, so take a few minutes and write those guys up. See what you come up with here. I want you to also do, if I took potassium chromate and mixed it with iron 3 chloride. All right, so that one too, balanced equation, total ionic equation, and net ionic equation, spectator ions. Yeah, let's take a look and see how we're doing. So I think I'll go to the next page here. So the first thing we want to do, obviously here, we're just given two things, sodium carbonate and barium nitrate. They're going to react with each other. So we want to start with the correct formulas. So sodium is +1 and carbonate is -2. So we should get something that looks like sodium carbonate like that, Na2CO3. We're going to react that with barium, which is +2, nitrate, which is -1, which should give us a little barium nitrate action like so. Yes. Any questions on that? We should also be able to recognize at this point that this is two ionic compounds. So that's a positive negative guy, right? Positive negative, which means it's going to be a double displacement reaction, which means the positive guy, which is the sodium, is going to hook up with the nitrate in this case. So again, we're going to get these guys to basically switch partners. Also, as we talked about previously, we want to make sure we start with the correct formulas here. So that's a sodium ion, which is +1, and a nitrate ion, which is -1, which gives us NaNO3, not Na2NO3 too. Yeah. So again, you do not want to balance first. You want to get the right formulas down. Once again, the barium is +2. Carbonate there is -2, which gives us a BaCO3. First off, any questions on getting the proper formulas down? So now that we do have the proper formulas, we then want to balance it. So again, you don't want to do both of those things together. So to balance it, it looks like perhaps we got a polyatomic ion there with nitrate. We'll lay up a 2. And I think we might be good at that point, I think. So we got 1 barium on each side, 2 nitrates, 2 sodiums, and 1 carbonate. So we're actually balanced. Any questions on writing this formula here? We also want to use our solubility rules here to figure out, is it aqueous? Is it solid? So looking at the first one, I got sodium and carbonate. Sodium is group 1. It is soluble in everything. There is no exception, which means I do not need to go any further than that. And I know that this guy is going to be aqueous based off of that. I could look at the next one, which is barium and nitrate. Although you may not be able to find both of them there, I can find nitrate there, for example. And that is soluble in everything, and there is no exception to that. So as soon as you see nitrate, you know that it's going to be soluble. So I know that that guy also should get the aqueous symbol. Any questions on that there? Now coming to my next one, I have sodium and nitrate, which is both of those guys together, which means you could really look at either one. But as soon as you see sodium, I know that this guy is going to be aqueous as well. Coming here to barium carbonate, I see carbonate here, which is insoluble. And the only exceptions is alkali metals, which is group 1, which barium is not a member of group 1, and ammonium, which that is not barium either. So in this case, I know based on the solubility rules that that is going to be my solid, and this is going to be the precipitation reaction, right? That's the precipitate that's going to be made. Any questions on how we use the solubility rules there? What we have up there right now is, again, the balance molecular equation, right? The next thing that we want to write is the total ionic equation, our complete ionic equation. We're going to break apart anything that is a strong electrolyte, and that's pretty much all the ionic guys. So that's going to give us 2 sodium ions plus a carbonate. That will also give us 1 barium ion here, as this is a strong electrolyte. Once again, this 2 will come to the front when we come to this equation. This 2 will also get distributed to everybody behind it as we break it apart, as sodium nitrate is also a strong electrolyte. So that's going to give me 2 sodium ions and 2 nitrate ions. And here our barium carbonate will stay together because it is a solid. Otherwise, it would be freely floating and would be an ion in this case. This equation right here is our total ionic equation, yes? Any questions on how we got to that one there? It is from the total ionic equation that we should be able to identify our spectator ions. And once again, we're looking for something that is identical ions on each side. Again, each of these things have charges that are ions that are written in this formula. If we look, we will see a couple of sodiums on the left to match the couple of sodiums there on the right. We will see a couple of nitrates on the left to match the couple of nitrates on the right. So our spectator ions here will be our sodium and our nitrate in this case. Any questions on how to ID those guys? So they got to be exactly the same on both sides. So they can't be attached to anything else. They got to look exactly the same. Because they're spectator ions, they're just watching the parade go by there. So we're just going to get rid of them. And that's going to leave us the last equation that we're looking for, which in this case is the barium plus the carbonate ion floating around. Will find each other and make barium carbonate, which is our net ionic equation. This is pretty much what is happening in this case. Those ions are coming together to make the solid, which again is really why this reaction is taking place, because a solid is being made. Any questions on any of those steps there? All right, then let's take a look at the other one there and go through the steps. So here we got potassium chromate. Once again, potassium is +1. and chromate is -2, which gives us this guy right here, K2CrO4. Iron 3 chloride is FeCl3, as iron is +3 in this case, chloride is -1, so we need 3 of them. Once again, from this arrangement, we should recognize this as a double displacement reaction. So we're going to switch our positive guys. That means the potassium and the chloride will come together correctly. So K is actually +1 and Cl is -1, which means we should have KCl. Again, no like K2Cl3 or some weird thing like that. Iron actually has a +3 charge, I believe, and the chromate's a -2. So we're taking a +3 and a -2 together. So to get the proper formula here is going to be Fe2CrO4 3 in this case. Yeah. Any questions on those formulas? Now that we have the formulas here, we want to actually go back and balance up everybody. So get rid of some of that. All right, so it looks like in this case here, maybe a 3 there, maybe a 6 there, maybe a 2 there. Yeah, we'll balance that guy up. Yeah. Any questions on that? Again, using my polyatomic ion there, starting with the chromate, 3 on one side, 1 on the other, and balancing it that way. We're going to use our solubility rules here. And once again, looking back on our chart, I see potassium, which is soluble in everything. So as soon as I see that potassium, I know that this is aqueous. I have iron 3 chloride in this case, and that is chloride, which is soluble in everything except for silver, lead, or mercury, and that's not iron in this case. So it is going to still be soluble. Soluble, which is not the S, it is aqueous. There we go. Potassium is group 1, which is soluble in everything, and that means it's going to still be here. And now if we come back here to our chromate, which is right there, it is insoluble, except if it's group 1 or ammonium. And in this case, it is not, it's iron. So that will be our solid in this case. Any questions on the solubility rules there? That is our molecular equation. So now we're going to break this apart. So this is a strong electrolyte. So that's going to give me 6 of the potassiums, as we do need to distribute this to everybody. That will give me 3 of the chromates. This iron 3 chloride is also a strong electrolyte. So that's going to give me 2 of the iron 3s. Once again, this gets distributed to everybody, so that will actually give me 6 of the chlorides when I multiply the 2 times the 3 in that case. Coming to this side, going to give me 6 potassium as I distribute this guy as well. And 6 of the chlorides. And this guy is going to stay together, Fe2CrO4 3, which is a solid. This is going to be my total ionic equation in this case. Any questions on that? My spectator ions in this case is which ones? It is the potassium, which is the same on both sides, and it is the chloride in this case, which is the same on both sides. So our spectator ions are those 2 guys. Potassium and chloride. We're going to once again cancel them out, and that's going to leave us our net ionic equation, which is 2 of our iron 3 coming together with 3 of the chromates to make this solid that's going to form. And that would be our net ionic equation here. Any questions on how to write equations, total ionic equations, net ionic equations, how to find spectator ions, use solubility rules, which again, you do need to know. Yeah. Any questions? Okay. So a lot of times we do look at net ionic equations in these type of reactions because again, it's basically showing us what's really happening in this reaction when we mix everybody together so that we can kind of get down to what is actually taking place. So what we just looked at is the solubility rules in terms of figuring out sort of what will make a solid, which is one of those reasons why a reaction takes place. The next sort of category, again, of double displacement reactions, as we talked about, are acid-base reactions, which fall under this category. Again, acid-base reactions are going to make water as opposed to a solid. But we could also explain what's going on in very similar terms in terms of these equations as well. So let's take a look at those. Acids, they have a sour taste. Don't eat any acids or bases in lab, right? But they do cause litmus paper to change color. If you have litmus paper that basically turns red, stays red, that means it's an acid. They react with certain metals to produce hydrogen gas, and a number of reactions that we've done before where you put your finger over the test tube and do the wooden splint type of move. So like a single replacement reaction when we take zinc and hydrochloric acid. Zinc comes in, kicks out the hydrogen, makes some zinc chloride and some hydrogen gas, which is the bubbles that you see in this particular case. Aqueous solutions, which are strong electrolytes, and also weak acids will also conduct electricity. Bases, on the other hand, are bitter taste. They feel slippery. They change litmus paper basically to blue. So if you have litmus paper that ends up blue or stays blue, that usually means that the solution is basic. They also are, as we talked about, strong bases or strong electrolytes, which will be able to conduct electricity. So the definition again of an acid is something that has the ability to produce H+ ions in solutions. H+ is the hydrogen ion. Hydrogen, as you will remember, has 1 proton, 1 electron, and no neutrons, which means in order for it to become positively charged, it had to lose its 1 electron, which pretty much leaves it just a proton. So H+ is the hydrogen ion. It's also sometimes referred to as a proton in acid-base chemistry. Also in acid-base chemistry, H+ and H3O+ are essentially equal to each other. This is what is known as the hydronium ion. It's kind of like a polyatomic ion. They both basically represent the acid part of the solution. So when you're dealing with acid and bases or acid-base chemistry, you can pretty much interchange H+ and H3O+, both in formulas and also equations. They're sometimes used like each other. As we talked about, that list of those kind of 6 strong acids, HCl, nitric, sulfuric, perchloric, hydrobromic, and hydroiodic acid, when they do go for a swim, they again are going to completely break apart. And because of that, for example, here with our nitric acid in solution, you have pretty much all H+ and NO3-. So when you have a solution of nitric acid, it has a ton of free H+ basically floating around. And that's the important part to make something an acid, is the ability to produce that H+ in solution. And it has to be free H+ that's floating around in order for it to sort of be an acid. So something that is strong, that's going to just break apart in solution, has no problem generating a lot of H+ really quickly, which is why it's considered a strong acid, because as soon as it goes in, you got a bunch of H+, in that solution will affect the pH of that solution and make it more acidic than it was before. Bases are things that have the ability to produce hydroxide in solution, which is OH-. And it's the same idea as the acid. It is the ability to produce OH- in solution. And things that are strong bases, because they are strong electrolytes like sodium hydroxide, potassium hydroxide. Pretty much if you look at the periodic table where lithium is, and you got sodium, you got potassium, you hang go right there to calcium and come down. Any of those guys in group 1 or 2 that has hydroxide in their formula, are pretty much going to be strong bases. And that's what group 1 and group 2 are. They're alkaline metals, they're alkaline earth metals. The word alkaline means basic. Means pretty much basic. So a lot of our strong bases come from guys in group 1 or group 2 that have hydroxide in their formula. Same idea with something like sodium hydroxide, going to produce a lot of OH minus really quickly. Not all bases have hydroxide in their formula, but they're able to produce hydroxide. So probably the most common weak base that you'll come across is ammonia, and ammonia is NH3. And when ammonia is in water, what actually happens is ammonia will actually pick up an H plus from water, and it will make some ammonium and some hydroxide, or ammonium hydroxide. And because it's able to produce some hydroxide, it's considered a base. It doesn't obviously have OH in its formula, but it's able to do this little reaction with water and produce hydroxide, which makes it a base. It's a weak base, which is why it has those arrows heading in both directions, like we talked about with the weak electrolyte, but it's still able to produce some OH minus in solution. Still considered a base, but it's a weak base. And that's different than a strong base, which pretty much all it has to do is go into the solution. You got a ton of OH minus. NH3 has got to go find some water, do a little reaction to produce some hydroxide. So it's not going to produce anywhere near the amount of like sodium hydroxide when it goes into solution. Any questions on that there? So when we take a strong acid and a strong base together, we always get two things. When we react a strong acid and a strong base together, we always get a salt and water is produced. Salt is an ionic compound, and water obviously is H2O. So for example, if we took something like hydrochloric acid and potassium hydroxide, it really is a double displacement reaction, plus and minus. The H plus and the OH minus will come together, and the chloride there and the potassium will come together. That will make KCl, which based on solubility rules is going to be aqueous, and that is our salt. And it will make water, which obviously is water here. That's our acid, and that's our base. So always what happens in a strong acid, strong base is the H plus comes from the acid, the OH minus comes from the base, and that's pretty much where water comes from. The other two ions come together to make the salt. We can write a total ionic equation for this. Because that is a strong acid, it will break apart into H plus and Cl minus. Because that's a strong base, it will break apart into K plus and OH minus. Potassium chloride is a strong electrolyte, which will break apart into K plus and Cl minus, and water is a liquid, which means it does not break apart, it stays together. So here we would want to keep water together. In this particular case, our spectator ions is the chloride on each side and the potassium on each side. Those are our spectator ions, which cancel out. And that gives us our net ionic equation of H plus from the acid coming together with the OH minus from the base to make water. And again, that is one of the reasons why a reaction takes place. So ultimately, if you wrote the net ionic equation for any combination of strong acid and strong base to come together, that is a net ionic equation you end up with. You end up with basically the formation of water, which is really why those things are happening. It's also why it's referred to as an acid-base neutralization reaction in that particular case. Question on that there. Now, just to show you the difference here to finish up on in terms of what we're talking about, that's what happens, obviously, when you take a strong acid and strong base together. Because the strong acid and strong base are strong electrolytes, we would break them apart. But let's say we did this same sort of deal with a weak acid like hydrofluoric acid and say sodium hydroxide. In this case, this is a weak acid. And how do I know that? It is pretty much not one of my 6 that was on my list. So this is going to be a weak acid. That's a strong base because that's like group 1 with hydroxide. So I know that's going to be probably a strong base. This is still going to be our double displacement reaction, positive, negative, which means the H and the OH is going to come together to make water. And our sodium fluoride will be our other guy that is made in this case as the sodium and the fluoride ion come together. That is our molecular equation, which is balanced. When we go to the total ionic equation in this case, because that is a weak acid, that is a weak electrolyte, which means it stays together. We do not break it apart. We do continue like normal. Our sodium hydroxide, which is a strong base, will completely break apart. When we get over to this side, our water will still stay together because it's a liquid, and our sodium fluoride will break apart because it's a strong electrolyte. And this is what our total ionic equation will look like, a little bit different because our weak electrolyte will actually stay together. Because of that, we end up with how many spectator ions in this case? We actually only end up with sodium as our spectator ion. It's the only spectator ion in this case. And that will still get canceled out like normal, which leaves us a net ionic equation that looks a little bit different because of the presence of the weak electrolyte. It will look something like this. The HF is going to react with the OH minus to make water and our fluoride. This would be our net ionic equation. So if you do have a weak electrolyte involved, you got to keep it together and your net ionic equation will look slightly different. Any questions on that? You'll probably only have 1 spectator ion. Questions?